Okay, let's now move on to perpetuities. Perpetuity is an annuity that makes eternal payments. So it's an annuity where capital T is equal to infinity. So we know what is the present value of a perpetuity. So it's the limit when capital T goes to infinity of the present value of an annuity. Since 1 plus r is greater than 1, 1 plus r to the power t is a number that keeps increasing as t goes up. And when t goes to infinity, 1 plus r to the power t is infinite. 1 divided by infinity is equal to 0. So the limit when t goes to infinity of the present value equation for an annuity is equal to c divided by r. If we are dealing with a perpetuity paying at the beginning of each year, the present value of this perpetuity is 1 plus r times the present value of a perpetuity that would make payments at the end of every period. There's another way, okay, to derive the value of a perpetuity. Okay, if I want to create a perpetuity, I have to deposit money in an account and only consume the interest of the account from now on. So the payment C would be generated by an interest rate applied on an amount of money that would stay in the account forever. So to generate C at the end of the first year, I would have to deposit P at the beginning of the year. So today I deposit P in an account that pays an interest rate equal to R. So by depositing P today in the account, I collect C at the end of the year, C at the end of the second year, C again at the end of the third year, and C forever. So P stays in the account. I never touch the principal, and I just consume the interests forever. So what is the cost of creating such a perpetuity? The cost of creating this perpetuity is is P. So I have to deposit P today, and I get my perpetuity. So since C is equal to P times interest, what is the value of P to generate C when the interest rate is R? So the value of P is C divided by R. So we obtain the same equation as taking the limit of the the finite annuity equation when T goes to infinity by looking at the problem this way, okay? Then when we take the limit of the present value equation when T goes to infinity. And we can also obtain the present value equation of a finite annuity by constructing it using two different perpetuities. Okay, so here we have perpetuity 1 that pays C forever starting next year, and perpetuity 2 pays C forever, but the first payment takes place at T plus 1. Okay? So P1 minus P2, that's the regular annuity that pays C over the next T years, right? So P1 is C, 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 C forever. P2 is C forever beginning at time T minus 1. So P1 minus P2 is equal to a payment of C over the next T years. So if I take P1 and I subtract from P1 what I've called P2, well, I removed from P1 all the payments C from time T plus 1 and after. So P1 minus P2 is equal to, so the value of P1 minus P2 should be equal to the value of an annuity making capital T payments of C over the next T years. Now C over R, what is it? It's the present value of a perpetuity one period before the first payment. So C over R is the present value of P1 at time 0. And C over R is the present value of the perpetuity P2 at time T, because I need the first payment to be on the following period. So when I'm standing at time capital T, the present value of P2 is C divided by R, the perpetuity equation. Now I want to compute a present value as of time 0, so I need to calculate the present value of P2 as of time 0. So since C over R is the present value of P2 when I'm sitting at time T, the present value of P2 when I'm sitting at time 0 is C over R discounted over T periods. And if we say that the present value of an annuity making T payments of C over the next T years is equal to the present value of P1 minus the present value of P2, well, that means the present value of such an annuity is equal to C divided by R minus C divided by R discounted over T years. And this brings us back to the present value equation we have obtained earlier in this course. Very good. So this is simply an alternative way to obtain the present value equation of a finite annuity by considering the combination of two perpetuities. Now, growing annuities. So suppose I have an annuity that will be producing T payments, and these payments will grow at the rate G every period. So the first payment is C, the second is C times 1 plus G, the third is C times 1 plus G to the power 2, and so on. So payments are growing at the constant rate G. What is the present value of such an annuity? So we will be using the same trick as before. So the present value of a growing annuity. So I've used this. We are using the subscript G to say that the perpetuity, the annuity is growing over time at the rate G. So the present value is C discounted over one period, 1 plus G times C discounted over 2 periods, 1 plus G to the power 2C divided by 3 discounted over 3 periods, and so on. I can isolate C over 1 plus G here. And what do we have in parentheses? 1 plus G over 1 plus R, 1 plus G over 1 plus R to the power 2, 1 plus G over 1 plus R to the power 3. Okay, so this is a geometric series. So something plus something squared plus something to the power 3 plus blah 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 plus something to the power t. Okay, always the same object to a different power. So if I take this object here, or if I use a if I multiply this present value here by something that relates to this object, I can simplify everything. Okay, I could have multiplied it by 1 plus G over 1 plus R. The manipulations will be faster if I multiply by 1 plus R over 1 plus G. Okay, so in fact what I'm doing here is I'm dividing PG by the object we are dealing with here. Okay, and then I'll do the same trick as before. One of the series minus the other, a whole bunch of terms will disappear. And that will give me, I'll be able to isolate PG, and that will be my solution. Okay, so PG times this term here, 1 plus R over 1 plus G is equal to C over 1 plus G times 1 plus G and so on. So if I take this term here, PG multiplied by 1 plus R over 1 plus G, and I subtract PG, 1 plus G over 1 plus R, 1 plus G over 1 plus R, this term disappears. 1 plus G over 1 plus R squared will disappear, okay, and so on. Okay, and so once I have this equality here, I can rearrange everything to obtain the present value of a growing annuity. So the present value of my growing annuity is C divided by R minus G. So the equation resembles a lot what we had without growth. But this is PG C over divided by R minus G times 1 minus 1 plus G over 1 plus R to the power T. So the present value, where the first payment will be C and payments will be growing at the rate G over the next T periods, is equal to C divided by R minus G times 1 minus 1 plus R minus 1 plus R over 1 plus G over 1 plus R to the power T. So the present value of a growing annuity is necessarily larger than the present value of a constant annuity. What is the present value of a growing perpetuity? It depends on whether or not G is smaller than R or equal or greater than R. So if the payment grows at a rate that is larger than the discount rate, the value of the perpetuity is infinite. For the value of the perpetuity to be finite, I need a payment that grows at a rate that is smaller than the discount rate. This way, payments into infinity end up having a present value of 0. Whereas if the growth rate is larger than or equal to the discount rate, so even though I'm discounting more and more payments which are going to be received far into the future, when I compute the present value, I always add up numbers that increase, okay, and that gives me a sum that is infinite. When G is smaller than R, limit when T goes to infinity of this term here is 0. When G is greater than or equal to R, limit when T goes to infinity of this term here is so here, when this is strictly greater than 1, when this is equal to 1, it's equal to 1. When this term here is strictly greater than 1, this sum here is infinite. So the limit when T goes to infinity of my growing annuity equation is equal to C over R minus G, only if G is smaller than R. Otherwise, if G is greater than or equal to R, my growing perpetuity here has an infinite value. The future value of a growing annuity. So if we are given a growing annuity making T payments growing at the rate G, what is the future value of this annuity at time big T? We take the present value equation, we compound it over T periods, and that's it. We're done. So as long as you remember the present value equation, you can always obtain the future value of an annuity. An example, a firm is expected to generate a net cash flow of $10,000 at the end of the year. Cash flows will then increase by 3% annually until the end of year 8, time at which the firm will be sold for $120,000. What is the present value of this firm? So what are all the cash flows produced by the firm? So there's a growing cash flow over 8 years plus terminal value at the end of 8 years. So the present value of a growing annuity for which the first payment is 10, growth rate is 3, and the interest rate is 11, plus the present value after 8 years of the terminal value. So this gives us in thousands of dollars 108.36. So $108,000, $108,360. This takes us to net present value, which I will see later in the course.